hospitals using stochastic simulation. And there's kind of two approaches, I think, to explaining a model. You can either start at the bottom or you can sort of start at the top, and that's the approach I'm going to take, is I'm going to start at the very output of the model. I think understanding where we're going helps you sort of understand the journey we're going to go on. So this is the dashboard, and I appreciate it's still relatively early in the morning and I'm flashing lots of numbers at you. So I don't really want you to take too much in. I just want to kind of quickly acquaint you with what I'm trying to produce. So on the left are the queues currently in the system for discharge pathways in a particular site in my system. And on the right are my forecasts. So these are 10-day forecasts for those separate pathways for the demand that I'm expecting. So if you're sitting in this position, you're able to look at what your queues are today, and you're able to look down the road by 10 days and anticipate demand. And that's the kind of like fundamental thing. It's about anticipating this demand to try and proactively procure capacity for it. So with that, I'm going to quickly show you the outline of the talk. It's pretty standard. I'm going to talk about the problem context and the aims. I'll move through into the methods. I'm going to talk about the data that's required to calibrate this model. And I'm going to go in quite a lot of depth about the model itself. It's quite technical. I'll then talk about how I've validated this model, and then I'm going to go into how I implement this model and also share how you might implement the same model yourselves, and then I'll move into the closing remarks. Cool. So the fundamental problem I'm trying to address is like the issue around elevated bed occupancy in the acutes. Now, there's many reasons for this, but the specific type of elevated occupancy I'm looking at is the occupancy due to patients that have no criteria to reside. Once they become medically fit for discharge, they might require extra treatment, but that could be outside of the acute setting. And this issue has up and downstream impacts. If you've got people in the beds that don't need to be there in the acutes, then new people can't flow in. That's an upstream impact. And downstream, the patients that spend too long in the acute setting have been shown to have this issue with deconditioning and actually getting worse. So it's a win for the system and it's a win for the patients to try and alleviate this. So basically you want this discharge process to be as sort of slick and as fast as possible. And one of the barriers to that timely discharge is the access to these intermediate care services. So these are these external services that are utilized for those patients that do need additional care, but that shouldn't be necessarily in the acute setting. This is called Discharge to Assess. And there are three pathways. In pathway 1, the patient is discharged to their home and they have daily home visits. And pathways 2 and 3 are bedded care, but in the community setting, so importantly outside of the acutes. There's also pathway 0, which is your no additional support, your default kind of discharge profile. Now, one of the issues is there's insufficient capacity along those pathways, but the patient requires them. So, for instance, if a patient requires a pathway 2 bed and there is no pathway 2 bed available to them, they must reside in the acutes, and this is where we get this elevated bed occupancy issue. So at that level, at that kind of capacity demand level, when you're looking at the aggregate of all your beds, you want to be able to understand what the demand for these pathways will be down the line in order to try and proactively plan for that situation. So with that, the objectives for my model are to forecast for the next 10 days the numbers becoming ready for discharge along each of those D2A pathways. Specifically, I want to be able to personalize those predictions for the patients that I know about. Those are those patients that are in there on the forecast day 0, the patients that are currently in the beds. I know lots of things about those patients. I know what specialty they're admitted to. I know their age. I know things about their comorbidities. So I want to make the best use of that data to make the most accurate predictions. But combined to this, there's another patient cohort that haven't even arrived at the hospital yet. In a 10-day forecast horizon, many of the discharges will be from patients that haven't even arrived. So I need to account for that by forecasting new arrivals, essentially. But those will have to be non-personalized global predictions. And I want to combine all of this and refresh these results to provide them to my operational colleagues daily on a dashboard, essentially. So those were the fundamental objectives of my model. Cool, so I'll move into the methods now. And I'm going to start actually with the data, because the model's relatively complicated, but in this instance, the data, I think, is actually quite simple, and I think that's a better situation to be in. It's worse when the model is simple and the data's complicated. So essentially, we have this flow called the NCTR daily flow, which is like a downcast of a national rep, so you should be able to achieve similar flows in your systems, which is essentially a daily bed census. At 10 in the morning, a snapshot is taken of all patients that have been in that acute bed for longer than 24 hours. And this captures their age, their sex, the admitted specialty, the bed type, their current length of stay, their CTR status, and their pathway outcome. And that is like if they're already on a queue or not, and that's what that relates to. And I link to this to a primary care attributes table, which is part of my system-wide data set that we have in our system, which is like a monthly census of all of the patients in our system, and it reports on various attributes of those patients. Importantly, it includes information about their comorbidities. So I'm not actually going to use the comorbidities themselves, but I use the comorbidities to compute a composite comorbidity score, the Cambridge score, which, if you don't know, is essentially like a single value, which is like an index for frailty. It's like the higher it is, the more frail the patient tends to be. So, the model itself. So, again, as I said, we're looking at where we're going. So if we look at the right, that's what I want to get to. It's the number of, it's the discharge readiness and the pathway requirements for these patients over the next 10 days. And to be clear, I'm going to do this, to say it in the simplest words possible, I'm going to predict that for these patients individually. So for each patient, I'm predicting the discharge readiness date and the D2A pathway as separate independent events. And this is a simplification for sure. These things definitely will have interactions, but just wanted to be clear that that's a simplification I'm making. Now, as well as there being two separate predictions per patient, there are two distinct patient populations. You have the currently admitted patients, and when I say currently admitted, obviously all of them are admitted at some point, but I'm talking about the patients that are admitted on day 0. And then there are these new admissions. So if you think about it, there's two types of prediction and there's two types of patient, so there's like a kind of quadrant, there's like 4 different types of unique prediction I'm making. In a kind of flow diagram, it can look like this. So I have the current inpatients on the top and the new admissions on the bottom. And step 1 is to forecast their discharge readiness. Step 2 is to predict their discharge pathway. I conjugate that, and then I aggregate that all up to get the answer that I want at the end. So I'm going to dive into those 4 quadrants now in a bit more depth. So when it comes to forecasting discharge readiness for the current admitted patients, these are those personalized predictions that I wanted to make because I know lots of things about these patients. So the fundamental engine I'm doing to estimate remaining length of stay is just using sampling from fitted distributions. The trick is that I'm fitting from personalized distributions. And I think the clever part, and this is if you're going to take one thing away, it's this little trick, is how I personalize those distributions. How do I make those distributions personal to each patient? So what I've done is I've taken my calibration data and I've passed it through a decision tree which is trying to predict on length of stay. Now, a decision tree itself doesn't predict length of stay very well, but what it does do very well is partition data. So if you can imagine that the decision tree sort of splits, say, on age, and then specialty, and the other attributes, at the end I have 16 leaves. And if I pass all that calibration through, the data that ends up in those leaves is very different. They have different mean lengths of stay, they have different tails, things like that. And I fit distributions at those leaves. And then when I have new current inpatients, I pass them down the same decision tree, find the leaf that they end up in, and sample from that distribution. One other subtlety is because I know their current length of stay, I sample from the remaining part of that distribution. I truncate that distribution when I sample from it, because that will mean that the expected remaining length of stay for a patient with a 1-day length of current stay and a 7-day length of current stay will be very different. When it comes to forecasting discharge readiness, for the new admissions, I must first forecast the new admissions. And I can achieve this with an ARIMA. It's a very off-the-shelf time series forecasting solution. And so I take those ARIMA-generated new admissions, I pour them into the simulation, and then I sample from a distribution to get their length of stay. I can't use personalized distributions in this case because it's a global population. I don't know anything about these. So I sample from the historical empirical distribution of all the lengths of stay I've seen in the calibration set. When it comes to forecasting the discharge pathway, again, there are 2 brands here. I've got personalized and non-personalized. For the current inpatients, I use those same attributes to train a random forest on the multi-class output of the discharge pathway. And then I can use that random forest on new patients in order to get the different pathway probabilities. And then again, I'm using weighted sampling on those probabilities in order to forecast their discharge pathway requirement. For the new admissions, again, I don't know anything about these patients, so I just sample from the historic proportions of those pathways. Now, you might be wondering how accurate those predictions are, and for any given patient, getting both their discharge readiness date and their pathway correct is actually quite unlikely. But this is the kind of beauty of stochastic simulation. I'm not trying to get the answer right for one patient. So I run this in a replication cycle of about 10,000. So I'm running about 10,000 simulations of this, and this allows me to capture for the large amount of variation in the number of arrivals, individual length of stay, and individual pathway requirement. And essentially, I can then take the average journey that every patient takes over those 10,000 different replications. And I can also capture the confidence intervals. How different did their journey turn out over those thousands of different journeys that they took? Cool. So that's the methods in a nutshell. So how do I validate this? How do I feel confident that I've got this right? And this has actually been a huge challenge. As I hope to explain, this simulation relies on fitted distributions, decision trees, random forests, simulation. I think there might be another one, but I'm probably forgetting it. However, lots and lots of things come together. It's quite meta. I don't think it counts as an ensemble model, but there's lots of components to this engine. And if I have the answer wrong at the top, it's very hard to know where I went wrong. So you have to take a bottom-up approach. You have to validate the very lowest level models, go up to the next level, validate again, the next level, validate again, the next level, validate again. Consequently, I have like a 14-page Word document going over this, and I don't have time to show all of that. So I have to be pretty editorial about what I'm showing here. I could show you really, really good results at the very bottom level. It's very easy to fit in ARIMA and make it perform well. And I could show you less convincing results maybe at the very top. I've taken the sort of tack of showing you the sort of intermediate range. And the reason why I might be wrong at the top, just to be clear, is that when you're comparing against real outcomes with real data, first off, I'm simulating an idealized world with idealized processes, and there's so many things in real data, data quality, operational, strange behaviors, bank holidays, Christmas, things that just get in the way and make it very hard to make these comparisons and fairly validate whether or not you're wrong because the model's wrong or whether or not you're wrong because the data's weird. So where I can, I'm trying to show you somewhere in the middle ground, something that's close to the reality, but it's not the full-fledged picture at the end. So when it comes to validation discharge readiness date, I can essentially compare simulated to actuals. So I can look at any particular day in my testing period. I can look at the patients that are currently admitted. I can roll the time forward, and I can see how they were discharged over the next 10 days. I can then run my simulation and compare those to the actuals. And these are the charts that you see on the right here. I've got that for both those populations. And you'll notice dips in the top graph there, two dips, and those are the weekends. These are the kind of real-life things that I'm talking about that are hard, that I don't want my model to replicate. It wouldn't be worth doing. But I hope that you can agree that this is reassuring that the dynamics are being replicated. When it comes to forecasting the pathways and validating the pathway model, it's a random forest, so I can just go to the on-the-shelf solution of using the ROC curve. I think we're probably all familiar with this. And I can tell you that I get an under-the-curve statistic of 0.81 to 0.84, which is good predictive accuracy. And more importantly, it shows that the model is really, because it's being trained on these attributes, those attributes lead to accurate representations of the probability of how that affects the discharge pathway requirements down the line. And I can also do the same thing with the actuals versus simulated. So this is now like what I predict as the discharge pathways on aggregate versus what I see on aggregate. And as you can see, I get good agreement there. Cool. In terms of implementation, I wanted to save quite a bit of space here. That we have quite a cool sort of DevOps stack in our system where we're quite unique, and I think that that allows us to do some things that I think other systems are trying to do, and so I wanted to kind of give an overview of what we do. So I've got quite a big diagram here, so I'll try and acquaint you with it. So on the top left is where the scripts are run, and this is, I have this Linux server, and I can embed these processes on a Docker. So this is a really nice way of operating, because I can just leave that on the server and it can be scheduled to run every day. And essentially the data flow comes into the SQL server and I then have my model scheduled to run a couple of hours after it's due to drop to kind of give it some lag to make sure it's arrived. And the discharge script run and it produces the output. Those outputs are then pushed to a SQL server where they're cached. And then the dashboard, the tool that I'm providing a link to at the end, only really queries that SQL server. This is kind of like, it's a simple solution, but it's quite a neat solution in the sense that none of the R code is ever being run on the Shiny server. There's no slowdown there. Like the model's being run in another compute instance, and whenever you refresh the Shiny server, you are always getting access to the latest answer. As well as this, I have a second Docker that I use to run the calibration scripts. So whenever I want, I can ping that service off, and I'm thinking about what the refresh schedule should be on this. I think every quarter I'll rerun this and allow those distribution fits and random forests to be retrained. This is really handy in the sense that there's often operational pressures to try and reduce length of stay, and if that length of stay does genuinely reduce and the system's now behaving differently, I would like my model to reflect that new behavior. So having a way of quickly recalibrating the system and having it pre-programmed to do that every quarter is a way of making sure that I'm keeping up the latest kind of behavior of the system. So I've brought us back to where we started, basically. So now I've kind of given you a whistle-stop tour of how the model works, and I wanted to quickly show you what the output is displaying in a bit more detail. So as I said at the beginning, we've got the current queues, and then we've got the forecasted demand over the next 10 days. And the dashed line there that cuts horizontally across is the 6-week average for discharges that have happened along those pathways. So this is a kind of like above and below the line, lets you know whether or not the queues are going to go up and down. Now, you'll notice that the vertical black lines are confidence bands, and you'll notice that they are very large, and this is because the numbers are very small. This is a really stochastic system, and you're basically simulating really small numbers. So although that might look a bit concerning about the accuracy, it's not really to do with the accuracy, it's to do with the fact that there's so many different kinds of things that can actually happen, and it's actually good to be able to capture the range of uncertainty that this system has by doing it this way. I've actually gone through that quicker than I thought. So I've got a bit of time to say that there's also another tab that I didn't think I'd have time to talk about, where I actually do the computation of, given that we hit 6-week average pathway discharges, and given that my model is correct, what direction will the queues go in? And I can add like 10% and minus 10% capacity on that, essentially shifting that dashed line up and down in order to see how that evolves. And that just kind of like really stops any of the kind of like ambiguity there. It's like, are the queues going up, are they going down? And what would a 10% increase do to say to that queue? So the last thing I want to talk about is that this is quite a complicated model, but as I mentioned before, the data requirements are quite simple, and I don't think that it's that unique that I have them in my system. I think you'd have similar in yours, and I'm really keen to share this model with other people. So essentially you've got, it's like ingredients, recipe, and meal, right? So you've got data, you've got code, and you've got what the output is. So in terms of, if you were looking to replicate this model in your system, essentially the data requirements are this daily bed census, right? And it's really important that it's same day. This is kind of maybe subtle, because people say, oh, I have daily bed data, and it's like, yeah, but it's a month out of date. You can't make a 10-day forecast on data that's a month out of date, so it needs to be something that's refreshed every day. It needs to be record level, it needs to keep the current length of stay, the bed type, the emitter specialty, and pathway outcomes. And I'm using about 6 months for that to calibrate my models. I don't know if you've heard of faster data flows. This is a kind of a new flow that's been trickling in. Like, I don't use faster data flows because we had this NCTR flow before, and I didn't want to migrate my code over to a new data flow. But I've looked at it, and they do essentially contain the same information. So if you are picking up that flow, I think you'd be able to calibrate your model and run it on that. And then patient attributes. In particular, I'm using age, sex, and the Cambridge score. But any comorbidity index would do as well, I'm sure. In terms of the code, well, the code is actually really complicated, which is why I'm happy to say that I am making it available to get on GitHub, which is obviously, as everyone knows, quite a nerve-wracking experience. I haven't had a lot of opportunity to make it particularly reproducible. It does really only run on my system with specific environment variables, etc. But there is lots of code that you can take and steal and repurpose for your own use. I do think there's lots of useful snippets in there. And of course, the code for this Shiny app is also there. But in a sense, it could also just be as simple as a PDF document output. It doesn't have to be a Shiny dashboard. It's just you can do it in your own way. So just to close, I won't iterate exactly what I've just gone over again about what we did, but we've developed a simulation. I am writing a paper about it, so that will soon to be coming. The code is open source. There's a link to it. By all means, go check it out. And I'm really happy to collaborate, so just reach out. You've got my email there, and come find me afterwards if you'd like to talk about it today. Thanks.
Thank you very much. You answered one of the questions, which is it available? Is the code available?
There you go,
So
yeah,
thank you. That's brilliant. Why do you need to forecast discharge pathways for patients you already have data on? Wouldn't this already be known?
So on a given day, there'll be many patients who don't have their discharge pathway known yet. They'll be maybe 1 or 2 days into their stay, and they haven't become medically fit for discharge yet. So I have it in the patient history, in the historical record, and I use that pathway outcome in order to calibrate the models to predict. But on any given day, there'll be many patients who haven't reached their no criteria to reside status yet, and they'll have to have an assessment before they can have their... I didn't go into this actually. I feel a bit remiss not talking about the assessment process. I've heavily simplified a very complex problem. Assessing these patients for what discharge pathway they require is incredibly complicated. You need to assess the patient's physical and medical and mental capabilities, and also their living conditions. So it's very hard to know that at any given day. I feel like I'm straying away from the original question, but there are many patients of which I don't know that, and yeah, that's why I need to forecast it.
Just to remind everybody, we're taking the questions on Slido, so the number is 3716942. You can upvote your favourite ones, but also if we can't answer them all today, then we can pass them on and they can be answered separately. Sure. So great work. Oh, sorry.
I don't know. There's a guy that...
There's 2 hands. Is the data being used operationally, and if so, how?
So yeah, it's a great question. We are socialising it within our system, and it is being used operationally. At least there's a drive to use it operationally, but however, it is actually really early in development. We haven't quite managed to integrate it, and I don't have any kind of good catchphrase outcomes for what decisions were changed, but that's the idea, is that this was requested by our operational colleagues, and I've produced it for them, and they're now sort of implementing it in their planning meetings. It has been shown, and people have basically asked me to validate it and make sure it's accurate. I've done that validation, I've passed it back to them, and we're kind of in that iteration cycle of figuring out how it plays into their plans.
I'm going to ask if they could be put onto Slido. I'm so sorry, it's just that we've got so many questions, and I'm sure we can keep this conversation going well after we've done this. So why did you use a random forest model?
Good question. Well, to be honest, I didn't consider many different types of model. I used the random forest because it, you don't actually have to do a huge amount of hyperparameter tuning with a random forest. Often the out-of-the-box parameters work very well. And it performs pretty well. I feel like the random forest tends to be the go-to benchmark classification algorithm that people tend to reach for, upon which you might then argue that XGBoost might perform better than. But having fit XGBoosts before and spent hours waiting for my cross-validation loops to finish, I just was satisfied with the performance of the random forest and didn't basically go any further. At least not yet.
There's some rapid upvoting, so thank you everyone for that. If operational people can see the demand coming, what can they do differently about it?
That's a good question, and I wish I had a really experienced answer there. From my understanding, they are able to... So actually, I'll tell us a bit of a story. We were working on this model in the background, but at Christmas, this NCTR problem was particularly bad. And essentially, we were asked by our operational colleagues, how much, if I can increase, they know how much it costs to basically procure extra beds, and they had a number in mind and a percentage figure of, if we can increase the capacity by X%, what impact will we have on these queues? Will we get these queues down by this? And we did a very static version of this model. It didn't involve any of this nuanced, personalized prediction. It was just a in and out their capacity kind of queuing based model, and that went down really well. So basically operational colleagues can use it to consider that, how much bang for your buck do you get for buying, spot purchasing extra capacity in those